So now we come to question number 4. What is the frequency of red light in sodium chloride whose wavelength is 650 nanometer is in vacuum? So we want to know what is going to happen to the frequency of red light when it goes from vacuum to sodium chloride. Well, one of the things we learn in optics is that when a beam of light goes from, let's say, vacuum, or we could even say air, because the index of refraction of air is very close to the index of refraction of vacuum. So then we say we have another medium here, let's say it could be water or some other medium. We learned that the beam of light bends inward, and the reason that it bends inward is that the beam of light slows down. V is equal to C over N. We did this in the previous problem, question number 3. So the velocity of light slows down in that medium, causing it to bend inward, okay? So now we want to know what happens to its wavelength and what happens to its frequency, right? So we have V is equal to lambda times F. We know for any wave, its velocity of the wave is equal to the wavelength of the wave times the frequency. So if the velocity slows down by a factor of n, what happens to its wavelength and what happens to its frequency, right? Well, if we imagine that this was the speed in vacuum, right? C is lambda F. We divide this by n. Which of these two should I divide by n? The lambda or the frequency? So it turns out that the property that is changed in the medium is the wavelength, not the frequency. The frequency of the light is what determines its properties. It's what determines if the light is, if we observe the light as red light, do we observe the light as violet light, as yellow light, as green light. So the frequency is the primary characteristics of the light that determines its color, because the frequency also determines its energy, right? The energy of the light is directly proportional to its frequency. So it turns out that a red light in air is also a red light in water or in another medium. So if they're both red, their frequency is unchanged, okay? So the frequency is unchanged, so the property that is changed in the medium is the wavelength. So we divide the wavelength by the index of refraction. So we have V in the medium, is equal to lambda in medium times the frequency of the light beam in vacuum. That one doesn't change, right? So in this case, we have 650 nanometer. The wavelength is 650 nanometer in vacuum, right? So we have C is lambda F, 3 times 10 to the 8th, 650 nanometer. A nanometer is 10 to the minus 9 meter. 10 to the minus 9. So let's find the frequency of this light beam in vacuum, okay? So we divide this by this, right? 3 times 10 to the 8th, divide by 650 times 10 to the minus 9. And what do we get? 3 divided by 650. 3 divided by 650 gives you 0.004615. 10 to the 8 divided by 10 to the minus 9 is what? Well, 10 to the minus 9 goes to the numerator, becomes 10 to the positive 9, and then 10 to the 8 and 10 to the 9 is 10 to the 17. And what's the units of frequency? Hertz, cycles per second. So if we change that to scientific notation, the frequency is what? You go 3 spaces this way, okay? So 1, 2, 3, 4.615 times 10 to the what? Well, since we went 3 this way, we have to subtract 3 from the power 10 to the 14 hertz. So the frequency of this light beam in vacuum is 4.615 times 10 to the 14 hertz. What is the frequency going to be in the sodium chloride or in the other medium? It's not going to change. It's going to be whatever it was in vacuum. So the answer is this one, 4.62. You see this one rounded up? 4.62 times 10 to the 14 hertz. The answer is B. Okay, what if the problem had told us this? What is the frequency of red light in sodium chloride whose wavelength is 650 nanometers in sodium chloride? So what if they had told us its wavelength in the medium? Okay, how would we answer it? So then what would we have to do is we have to use the velocity of the beam of light in the medium, right? So we would have to change this, divide this by n. Well, the rest of it stays the same. So change this to V, right? You go 3 times 10 to the 8, n. We would use the 650 again. The 650 would come down here again. I would have an n. So then basically what would happen is I would have to divide this answer by n. The frequency of the light beam would equal what? 4.615 times 10 to the 14 divided by n. N is what? Well, then we would have to use the index of refraction of sodium chloride, which was given in the previous problem, question 3. So I would put here 1.53. So then you would do 4.615 divided by 1.53. And the answer would be 3.016 times 10 to the 14 hertz. Is there that choice? 7.06, 4.62, C. 3.02, 3.016, 3.02 times 10 to the 14 hertz. So depending on the wording of the problem, is the wavelength given in the medium or is it given in vacuum? Then from there you can calculate its frequency, and the frequency should be constant whether it's vacuum or sodium chloride. So this kind of problem pretty tricky, okay? You could go wrong very, very easily. You have to pay attention to the wording. So in this case, the answer was B. Okay, thank you.